kind of an interesting one. Interactive system intended to operate in parallel with the electric utility, and to me in the non-electrical engineering world, I'm thinking, well, two parallel lines are running side by side to each other but never touching. What they're meaning, paralleled series wiring versus parallel wiring. When you're AC coupling inverter to the electric grid, which is basically when you're connecting any inverter to the electric grid, that's an interactive system. And says to supply common loads that may deliver power to the utility. There are one-way inverters that don't, at that point of interconnection to the grid, feed any power out of that point. It might just be a one-way charger, and the inverter might have a separate output somewhere else for feeding a critical load panel. So like a UPS system, a battery system that protects your computers when the power goes out, that's a one-way inverter that charges from the grid but has a separate output. So a battery charger for your power tools has a battery and an inverter, but it's one-way electrical flow. It's not interactive. You can plug that into the wall and charge it. An interactive inverter is one that can output power to the utility. Dry locations and wet locations are pretty obvious. Maybe what's less obvious is slabs or underground would be a wet condition. Damp is a special wet condition where it's protected and under some awnings, and that can be useful in solar. There's a cable that I like called MC cable. It's a metal clad cable. We'll get to it later. But MC cable specifically is only rated for damp locations, so it can't go. There's only specific spots where it can be outside. And what that means is if you're coming out underneath a soffit, you might only have a couple of inches on the outside before you have to go into a box so that the soffit is still protecting that cable. And if you're in a very rigid jurisdiction, you might have to make that transition before you come out of the soffit, although flexibility does have its uses. And so you have to know, like, is the attic a wet space or a dry space? The attic is considered a dry space. Right above the attic is considered a wet space. And so you have to take that into consideration when you're transitioning from the dry space to the wet space. You're putting in good sealant for one. Solar is a hot environment. It's a wet environment. It's electrical equipment, so it needs adequate service space and clearance space. It can be hard to fit a complete solar system with a solar array and a battery in a control room because of the clearance requirements. So anyway, rather than just read more vocabulary, we're gonna come back to this. Well, okay. I guess we need to do a little bit more highlights. Let's see. NEC defines used equipment as reconditioned equipment. So that's pretty interesting because actually the commercial solar tax credit can qualify used equipment for the tax credit, provided that only 20% of the equipment is used, 20% of and 80% is new. So there's kind of a reconditioning or refurbishment that is built into code and also comes up in other arcane rulemaking processes. Sealable means, capable of sealing or locking so that live parts cannot be accessible without opening the enclosure. All right, let's get into some more pictures. All right, so installation requirements. Equipment that is listed, labeled, or both. So the important thing is listing and labeling are not exactly the same thing. Labeling the requirement might just be to field label it, to say, hey, add this information to whatever you installed. Whereas listing would say, hey, whatever you installed, has to be specifically called out to be for this purpose. So a slight difference in nuance between the two. Installation torque values, they're putting in code, an approved mean shall be used to achieve the indicated torque value. So this is a big update. Basically it says you have to have a torque wrench on site to complete your cable termination torquing. And I would say not all solar installers have torque wrenches on site. They rely on their, I use my hands, and I know what a tight connection is. Code now says have a torque wrench. Okay, working space. I don't memorize all the working space requirements. Basically what I do is imagine a person standing in front of the equipment working and to say, is this comfortable or not? At first glance, it could seem like this air conditioner is sharing the same spot as the electric service panel, but it's actually not. There's a 6.5 foot dedicated space vertically for your electrical equipment from the floor, or from wherever it starts. And so 6.5 feet up, really the only, aside from, how some of this data cabling and stuff looks, the code violation of this room is actually the buckets that could be easily moved. You have to have dedicated space for your electrical equipment so that you can stand in front of it and work in it comfortably. A lot of code violations are, in terms of planning, are readily apparent to visual inspection. Here is a box, and you have to lean over some batteries, which kind of have, they have some, shelter on them, but no bones about it. These are live terminals right here and right here. And you have to lean over those terminals to access this panel. And okay, on the one hand, it could be easy to see how they got here. They just had a very limited amount of space, but that's a safety hazard. So in code, it says you can only have a 6-inch relative depth between one piece of electrical equipment and another piece of equipment that's above or below it in that same space. And so I don't know, sometimes that can come into a room layout planning, like if you have a gutter and equipment that sticks out far from the wall, you may need to have the gutter offset from the wall a little bit. Mainly what I see is with these floor mounted batteries, like this case, you got to watch out for. So 6-inch depth, 6.5 feet height. The width requirement, this is the easiest one. The width of the space, it almost never becomes an issue. The only issue would be outside, is if you have like a gas meter and you're up against the wall or the edge, how far apart from the inverter can you land that gas meter? There's, as far as the electrical side goes, and some jurisdictions have larger requirements, but as far as the electrical side, it says 30 inches of dedicated space, or the width of the equipment if it's any wider than that. And so how I remember that 30 inches, again, it's just what could one person standing in front of the equipment, it's a terrible person, but 2 feet is not enough space for a person to squeeze in front of that electrical box and do any work. They need to be able to stand in front of it and work on it safely. It's about 30 inches wide. It's not 3 feet wide. Electricians are not 3 feet wide, but they need more than 2 feet. That's 30 inches. 6.5 feet tall, not leaning over more than 6 inches. The one that can be a little bit tricky is the depth requirement. Not from sticking out relative to other pieces of equipment, but from the dedicated kind of floor space that you need without something being behind you. And it's really weird because the rule is if you don't have anything behind you, then that depth is 3 feet. And so if there's nothing behind you, you need 3 feet of clearance space. It's like, well, how if there's nothing behind me, I have infinity clearance space. Okay, well, that means like things like those mop buckets and stuff can't be within 3 feet of the panel. However, that becomes a larger requirement if there is something behind you. So code says if there's nothing behind you, 3 feet, but if there is something behind you, we're going to step up the requirements. And actually, the requirements are different if it's 150 volts up to 600 volts, such as, so if it's a 120 volt service panel, if it's a 240 volt service panel, or if you're getting into like commercial systems. And so what I think about is I just worry about the residential requirements, and then I assume the commercial requirements may be more stringent. And so when I'm thinking about room planning for 600 volt, solar equipment and associated equipment, as far as that clearance space goes, it's 3 feet if there's nothing behind you. It goes up to 4 feet if there is something behind you. And there's also a middle condition. So there's a condition for if you're backed up against electrical equipment, or if you're backed up against an insulated wall, or if there's nothing behind you at all. And so you get into the higher ranges if there's electrical stuff behind you, and the shorter ranges if there's less stuff behind you. And so when I'm thinking about code and electrical room planning, I'm thinking about, well, what's the spaces between the equipment if we have a piece of floor mounted equipment and another piece of floor mounted equipment? Well, you would need 4 feet of space between the two pieces of equipment because that's something that's driven by the early sections of National Electric Code. Now, you might even say, well, what does that mean for spacing around the solar panels themselves? What I can say to that is I guess the whole array is considered one unit because there's not 4 feet of space between the individual rows on solar arrays. I like it when there is space for accessibility, but the standard is to cover most of the roof and only have walkways every 120 feet. Okay, so some other notes. We talked about the dedicated space. We talked about locking the enclosure or the rooms. We're seeing requirements about physical protection. And even more strict requirements the higher the voltages get. Once you go above a certain amperage, they start governing the way the door opens on the room that the equipment's in. Even larger than that, you might need 2 entrances in the room. Okay, so it says listed interactive inverters shall be permitted to be connected to premise wiring without a grounded conductor, where the connected premise wiring includes a grounded conductor. Well, what does that mean? Maybe it's a typo. I can't have this be a verbatim thing of code, but what I think it's saying is this. Air conditioning equipment sometimes does not have a neutral. And I said, well, you need that neutral to be the return path. Well, there's a special case, and that special case is when you have, a 240 volt circuit, which is actually two sine waves that are equal and opposite each other, and so they always have that 240 volt potential already. And so the nature of the 240 volt potential, it's 120 volts up and 120 volts down. We have that voltage potential, and voltage can flow across those two phases. And because these two phases are perfectly balanced, and so the air conditioner is drawing its power from both phases equally, whereas you might have on an electric service panel a different load on the right side of the panel versus the left side of the panel because they're doing different things at different times. An air conditioner is using that 240 volt circuit uniformly. And so they say, okay, well, in that case, or not in that case, in the case where it's a non-uniform load, where one load is smaller than the other, the neutral wire balances out the two loads. It shuttles off the difference in the load back to ground. But the air conditioning unit's perfectly balanced, and a 240 volt solar inverter is perfectly balanced, and most 240 volt devices, by nature, are perfectly balanced. And so sometimes 240 volt devices don't have a neutral wire because they don't need them. And so what this is saying is that actually solar inverters that are 240 volt do not need a neutral wire, and that all the more says that this can be a point of interconnection on a home, which I think is really interesting, because what that implies is you can put a just 4 or 5 panel system next to your air conditioner, maybe backfeed with microinverter circuits, or even do a kind of a critical load panel and back up your air conditioner while also backfeeding the grid. Like, it's a ripe opportunity for smaller, kind of ambitious do-it-yourself type projects. And it's allowed by code. And so some inverters will actually have a programmable setting on them where you can say, okay, well, this is 240 volts with a neutral. This is 240 volt, without a neutral, and there's other stuff going on there too about matching the electrical load. So some inverters can be configured to work with or without a neutral. And now we know it's because they're both legs are in perfect balance. And while we might not fully understand what imperfect balance means, we can understand what imperfect means. And if one side of the inverter worked harder than the other 120 volt leg, it would be imbalanced, but that's not how it's designed to work. Okay, so number 4 cable shall be identified over 60 volts, shall be identified at all terminations and splice points by tape, tagging, or another improved means. What that means, if it's smaller than number 4, the code compliant method is to use colored wiring. So that's when you have a red wire or a black wire or a white wire or green wire. So when it's all number 6 and down. Otherwise, you're allowed to identify it by colored tape. And it says number 6, we're not serving as the connection point for a grounded conductor. what it's saying is we use red for positive and black for negative on the DC side of things. And what that means is solar installers, you can have an installer that buys they're commonly using number 10, commonly using number 8, sometimes number 12. Those solar cables, they come in colors, and they also just come on a black spool. And if you're in an area where you have a very rigid electrical inspector and inspection, usually if you're in that area or not. They have, they might have solar specific inspectors. They may have solar incentives that come with additional oversight. Red for positive, black for negative on a DC system. Just like we were talking about imbalanced load, that it's now coming back to addressing, saying, hey, we want you to distribute branch circuits as evenly as you can along electric service panels. And now we have a requirement for arc fault current interrupter protections in readily accessible locations. And so that's been a relatively new invention and device, is arc fault current detecting circuitry. And you can imagine that if it's harder to detect a ground fault than it is an overcurrent instance, then it's going to be even harder to detect a smaller instance with less amperage in terms of a arc fault. And so those breakers are new. I think more basically with breakers, we can learn a lot about sizing by just noting the sizes that breakers come in. We have smaller breaker groupings, but then as the breaker sizes get larger, this grouping starts to separate. And so when we're linking the breaker size to our circuits, we have to do a couple of things. One, we have to look at the ampacity of the load, and then we have to apply some safety factors, and then that's the size of the wire, and then we have to look at the size of the breaker. So the question is, like, if I have a load that is 16 amps, and then I put it in I size the actual load might be 12 amps, and then I apply my over circuit protection for 16 amps, and then I go and I look at, well, what's the cable size I need for that? If I go and I put it on a 15 amp breaker, that won't work. The breaker will trip. So the question is, how much do you upsize a breaker for? And you're upsizing, because you can't get precisely, a 16 amp breaker. When these options start spacing out and you start getting into larger and larger circuits, you may actually take the load and take your cable size and have the breaker be somewhere in between, so that the load interrupts before. So that the load that is possible to go through that cable cannot possibly exceed the ampacity of the cable. At any rate, we're going to start developing how to size a cable for a load. And the fundamental building block is that you size the cable for non-continuous loads plus 125% of continuous loads. And so continuous loads are treated a little bit differently than non-continuous loads. So why is that? Well, continuous load is one that's always on, on for 3 hours or more. And so the cables of that continuous load are going to be operating at a higher temperature than that of an equivalently sized but non-continuous load. And so, we're saying, hey, continuous loads have higher operating temperatures, and so they, right off the bat, they need a 25% oversize in terms of amperage. And that is just a common, if you're shooting from the hip and not flipping through your code book and identifying what the oversizing is, the general case is you take the amperage and you oversize by 25%. Now, then we're going to learn about some additional points, but basically, when you apply all the special factors on top, your starting point is assuming whatever the load is rated for. You're adding 25% on top of that to make sure that the cable is not itself going to overheat. Make sure that you're giving some headroom in that cable ampacity so that when the system is at its full load, it's not overheating. So the overcurrent protection device should be not less than the non-continuous loads plus 125% of the continuous load. And so you take the continuous load, you add 25%, and then you round up to the nearest breaker size to get your breaker selection. So the cable itself is sized for 125% of the continuous load, and then the breaker is the next size up. So when you look at your breakers and you say, okay, well, that's a 15 amp load, that's a 20 amp load, and you look at your receptacle ratings and the receptacles are rated for 15 amps or 20 amps, that means you still have to put a smaller load into the actual load or real load into those receptacles. If I put a 15 amp load into a 15 amp receptacle that's on a 15 amp circuit, it would trip immediately, and it might trip, on the breaker side of it too, depending on where in that 25% extra headroom, the real amperage of the device lay. Let's see. So, there's some special exceptions, but in the interest of time, we're just going to keep moving forward. Then we have some requirements for power outlets being spaced 6 feet apart. The idea being that you're not having people use anything more than a short extension cord to power things inside their homes. Outdoor power outlets, one readily accessible outlet at the front and the back of the building. It's kind of one that threw me for a loop because I know not all buildings have that. So then we get into feeder circuits. So we said feeder circuits are what supply a building with power. They're rated for non-continuous loads plus 125% of continuous loads. Well, it's pretty standard stuff, and really there shouldn't be much interesting, special cases going on with feeder circuits. So the neutral wire has to be in the same enclosure of, let's see, we have identification of feeders where the premise has feeders for at more than one nominal voltage. Each ungrounded conductor shall be identified by phase at all termination points, connections, and splice points. This is kind of forming the basis of labeling all of your solar boxes, because that solar circuit, I would call it a feeder circuit. They call it a special photovoltaic output circuit. But still, you have to label the boxes and the conductors. Feeder circuits have to be similarly kind of over labeled. So we have a definition of voltages, and I would just remind you that when we talk about voltages, we're talking about nickname voltages, and the actual voltage versus the nickname can vary rather substantially. It's common for rural electric grids to operate at higher voltages than this to get 124 volts per leg and get up to 248, sometimes 250 volt readings. So these voltages are kind of nickname voltages. Likewise, we're not too concerned about math. Um, National Electric Code is a cheat sheet for making real engineering real engineering calculations. So we're not worried about significant figures or anything like that. It's where we're overestimating the safety requirements in order to enable just regular electricians to pick out the appropriate material without being engineers. And similarly, fractions of an amperage can be rounded to the nearest whole amp. Now, on a label, when it says you have to list the volts and you have to list the amps, you don't list the decimals. You just stick to whole numbers. And so here we have some general lighting load calculations. We kind of talked about this in the changes. But basically, if I'm designing a home and I want to start estimating what its energy usage is, I actually don't do it this way. I go find, electric bills of similarly sized buildings and kind of go into it that way. But there are general assumptions being made at how much power per square foot particular electric loads need to be sized for. And that is useful so that you don't get thrown for a loop from one building type to another. We also see that these load calculations are substantially reduced the larger the facility gets, because it's assuming that not all of those loads are going to be on at the exact same time, and it's seeing some benefit from aggregating multiple users onto kind of one grid feed. And so these tables have been substantially updated for NEC 2020 in terms of the lighting loads being significantly reduced. So that, if you're doing generator calculations and you need to know how large your generator is, you'll go in and use this table to come up with, wattage requirements for those loads. Finally, we have energy code permitted to be calculated using unit values specified in code, provided that there's automatic actions to reduce the connected load, and that the continuous load multiplier of 125% is applied. So I guess the reason I'm trying to mention this is there are minimum power requirements for buildings and structures. You might be looking at wanting to build an off-grid structure, and you say, well, batteries are real expensive, inverters are really expensive. If I just do everything perfect and select all of my appliances to keep my home power draw under 3 kilowatts, can I get away with a 3 kilowatt power supply? Can I run a house off a 20 amp circuit? The answer is no. Code requires, pretty much comes out to like 100 amp service at a minimum for dwellings, and then it goes up from there. And we even see that in later sections that we'll get to tomorrow, that way down in the specialty section at the end, when we're talking about standby and emergency power generators, that they have to be rated for the loads that they're going to supply.